Welcome to this tutorial on the shapes of molecules and ions. What I'm going to do is show you this master plan that I always use, this master diagram. My students find it very helpful because whatever the molecule or ion you're considering the shape of, if you run it through this procedure, you'll be able to work out the shape of it. Now, just before I get started, I want to apologise for all the faffing about I'm going to be doing, finding bits and pieces, models that I want to show you, but these are very helpful to help you appreciate the three-dimensional shapes and bond angles of these molecules and ions. Now, the first thing you do when working out the shape of a molecule or ion is consider the total number of electron pairs around the central atom. And I've underlined the word pairs because you must always talk of electron pairs, particularly in the exams. And this is to include bonding and lone pairs of electrons. So if we take, for example, the methane molecule, just drawing a flat structure on paper, if you like, would look like that, but of course the bond angle isn't 90 degrees as shown here. The first thing we need to do is have a dot and cross diagram showing the chemical bonding in here, showing the bonding pairs and any lone pairs. So carbon of course comes with 4 electrons in its outer shell, and each one forms a covalent bond with a hydrogen atom. And so there are 4 bonding pairs of electrons and no lone pairs, so in total we've got 4 pairs of electrons, and so it's going to come down this column here. So for methane then, it's the example to remember when you have 4 bonding pairs, I'll just put BP, but no lone pairs, and that's CH4. Now, the central guiding principle on determining why or explaining why molecules have the shapes they have is that electron pairs repel. Okay, electron pairs repel each other, and molecules and ions are the shapes that they are because in those shapes, by taking those shapes, they're minimizing the repulsion between electron pairs. I can show this very well in this model of methane, which I hope you can see properly. This cork in the middle is meant to be the carbon atom, and then we've got the 4 hydrogen atoms at the ends of the cocktail sticks, and the cocktail sticks are the covalent bonds, and on each little piece of card on here, hopefully you can see that each one has got 2 dots. That's the pair of electrons, and it's these bonding electrons that are trying to get as far away from each other as possible. So they can get as far away from each other as possible by adopting this shape. They get as far away from each other as possible, of course, because they are regions of negative charge. Like charges repel, so the region of 2 electrons is a region of negative charge, another one here. They all get as far away from each other as possible by adopting this shape. Now, I have here a molymod model of the same shape, and the way to describe that, well, it's called a tetrahedron, and the reason it's called a tetrahedron, or the way I would ask you to think about it, is imagine you were to wrap that up as a present for someone, and what would it look like if it was wrapped up with a minimum amount of paper? It would look like this, and it's a tetrahedron. It's got 4 sides to it, tetra, and each is an equilateral triangle. So the methane molecule is the one to remember for when you have 4 bonding pairs of electrons, no lone pairs, and it forms a tetrahedral shape. So I'm just going to write that down. It's tetrahedral is the name of the shape. I'll do it in a different colour. So it forms a tetrahedral shape. And the way to represent that on a flat surface, but to show that it's 3-dimensional, I'm going to draw it like this. Now, these solid lines represent bonds that are flat on the surface, they're in the plane of the paper. So if I take, for example, my diary, you can see that these two bonds, which are these two, they're flat on the surface, and then I've got another one that goes behind the paper, or the diary, and one that's coming towards us. So the one that goes behind the paper is the dotted line, and the one that comes out towards us is shown by one of these wedges. And while I've got this up here, you can see what the bond angles are. Those bond angles are 109 degrees, so it's the bond angle between this carbon and this hydrogen and the carbon and this hydrogen. That's 109.5 degrees. I'll write that down. So 109.5 degrees, and you do need to learn that as being the bond angle in a tetrahedral molecule or ion. Now, if we imagine you were to remove one of these hydrogens, we could still have 4 electron pairs around the central atom, but 3 of them are bonding and 1 of them is a lone pair. And the best example of that is ammonia. So I'll add this to this column. So we've got 3 bonding pairs and this time 1 lone pair. We've still got 4 electron pairs altogether. So ammonia has this structure. The nitrogen has 5 electrons in the outer shell, and then we have 3 hydrogens forming 3 covalent bonds, and then we've got a lone pair sitting on the top. So the lone pair is this pair here, sitting on the top of the molecule. Now, when that was a model of methane, this pair of electrons was halfway between the carbon and the hydrogen, approximately. But if we've taken away the hydrogen, then this pair of electrons is now much closer to the nitrogen. So as they move down, they're repelling these electron pairs. So these all move down to get away from the lone pair of electrons. So this bond angle decreases and it goes down to 107 degrees. So here is another model of this. The blue atom, of course, is the nitrogen. We've got the 3 bonding pairs, the grey sticks, and the lone pair sitting on the top. Because the lone pair's directly on the nitrogen, it's pushing these down, contracting that angle from 109.5 that you would have in a tetrahedral shape to 107 degrees here. And if I was to wrap that one up, I would get a pyramid. Okay, and it's a triangular based pyramid, so it's called a pyramidal shape. So the geometry of the ammonia molecule is pyramidal and the bond angle is 107 degrees. So let me show you how to represent that on paper. I draw the nitrogen with its lone pairs on the lone pair of electrons on the top. I just put any one of the bonds in the same plane. So let me show you with my diary again. Let's say that I put this nitrogen to hydrogen bond on the plane of the paper that I'm drawing, and I've got one coming towards me, that's a wedge, and one going away, and that's the dotted bond. So it doesn't matter which order you put these in, as long as one's dotted, one's a wedge, and one's solid, then that's good enough. So the shape this time is pyramidal, and the bond angle now is 107 degrees, 107 degrees. Okay, and you need to know that bond angle again. The effect of the lone pair is to reduce the bond angle by 2.5 degrees. So if I take another molecule in which I have replaced yet another one of the bonding pairs with a lone pair, I'll do it over here so that you can see it properly. But this time we're going to have 2 bonding pairs and 2 lone pairs. So we've still got 4 electron pairs in the around the central atom, so it's still coming down in this family, all derived from the tetrahedral shape, but successively replacing 1 and then 2 of the bonding pairs with lone pairs. And the example of this one is the water molecule. So water, the oxygen in there has got 6 electrons in its outer shell, and there they are, and you have 2 hydrogens, so 2 covalent bonds. So I can also represent it like this. So we've got 2 bonding pairs and 2 lone pairs, and we can think of the geometry of this one. So I'm going to remove another hydrogen, and now you have to imagine that this central atom is oxygen, and these are the 2 hydrogens, and then this pair of electrons will also be a lone pair close to the oxygen, and so you get even greater repulsion. So these bonds are pushed further down, so this contracts or decreases this bond angle down to 104.5 degrees. So here is the shape of the H2O molecule. You can see it's a V shape, but it has various names. I'll just draw the structure up here for you to see it properly. We've got 2 bonding and 2 lone pairs. The shape is, depending on the exam board, it can be V-shaped, it can be non-linear, sorry, that's non-lean, isn't it? Linear, non-linear, or it can be bent, depending on the exam board. So you can check that quite easily in your textbooks or the specifications. And the bond angle is down at 104.5 degrees, 104.5 degrees, because for each lone pair we remove 2.5 degrees, going from 109.5 to 107 to 104.5 degrees. So they're all part of this family of 4 electron pairs in total around the central atom. Now just a little word on the sort of language you have to use in explaining these shapes in answers in the exams. Let's just put all these in their place. That's the tetrahedral, that's the pyramidal, and that's the V-shaped. If we start off with the methane, what you've got to incorporate in your answer if asked to explain the shape of this one is to say that there are 4 electron pairs around the central atom, no lone pairs. You then say electron pairs repel, and in the tetrahedral shape that minimises electron pair repulsion. It allows the electron pairs to be as far away from each other as possible, minimising their repulsion. If you're asked to explain the shape of the ammonia molecule, again you have to say that it's got 4 pairs of electrons around the nitrogen, but you must say that 3 of them are bonding pairs and 1 of them is a lone pair. You then say that electron pairs repel, but very importantly lone pairs repel more, and this is why it takes the shape of the pyramid, the pyramidal shape. Similarly with the H2O molecule, you must point out that there are 2 bonding pairs and 2 lone pairs, which are here, and again you say electron pairs repel, but you must also say that lone pairs repel more, and so by taking this shape the electron pair repulsion is minimised. Okay, so that's the general idea. I've done it just for the 4 pairs of electrons around the central atom, and but we can do a follow a similar procedure for when we have 2, 3, 5 or 6 electron pairs around the central atom. And I'm just going to show you the main examples of those, but the principles are just the same. Okay, so we'll start off with 2 electron pairs around the central atom, and the example given in most of the textbooks is beryllium chloride. So beryllium has 2 electrons in its outer shell, and it forms 2 covalent bonds with chlorines. Now it's very important, if you're asked to draw the dot and cross structures of these molecules or ions, not to forget that you've got lone pairs of electrons on the chlorine as well. So that chlorine altogether has got 7 electrons in that particular shell. But these electrons, they don't control or determine the shape. They would have an effect, but you're not concerned with that at A level or at AS level. So beryllium chloride, we could write it like this, but we're really concerned with the number of electron pairs around the beryllium, the central atom, the atom about which we are considering the geometry, the shape. So there are 2, and they're both bonding, and the shape, as you can see, is a straight line. It's linear, and the bond angle is 180 degrees. It's just a straight line. That's, again, it's that shape because by being that shape you're minimizing the repulsion between these electron pairs. Now if I took away one of these atoms and replaced it with a lone pair, then you wouldn't be able to define a bond angle because you need 3 atoms to define a bond angle. So that's a very simple one, not much to say about it. Now the usual example you have for having 3 electron pairs around the central atom is boron trifluoride. So the boron comes with 3 electrons in its outer shell, and it forms 3 covalent bonds with the fluorines. And again, if you're asked to draw a dot and cross, don't forget the lone pairs on the fluorines. There they are. So again, I can just represent it like this, where it makes it easier to see the shape. And so we have 3 electron pairs around the central atom, and they are all bonding pairs. So I can just write here 3 bonding pairs, no lone pairs. And boron trifluoride, it minimises the repulsion between the electron pairs by forming a flat triangle. Okay, so it's called a trigonal planar, and we can work out the bond angle. It's basically, if you imagine you've got a pizza or a cake and you're dividing it into 3 equal slices, then 360 degrees divided by 3 gives you 120 degrees. So the bond angle is 120 degrees. Now with this one, it is possible to come down the family and have, you could have 2 bonding pairs and 1 lone pair. So you might find some strange ions in exam questions such as that. And let's just say the element, the atom in the centre is element X, and let's just say we've got a fluorine here and a fluorine here. I'll get rid of that. Then we have a lone pair of electrons on here. So we've still got 3 electron pairs around the central atom, but this time 2 are bonding and 1 pair is a lone pair. And as I think you can imagine, if that's the boron trifluoride, if we remove that bond, the electrons here, they move closer onto this atom, so you get repulsion here. So this bond angle decreases. And again, if you were asked to predict what the bond angle would be, you would take 120 and take away 2.5. So if you said about 117.5 degrees, you would be fine. Now before we do 5 I'm going to do 6 because it's easier to see the three-dimensional shape with 6, and the example here is SF6, so it's sulfur hexa fluoride. And first of all I'll draw a dot and cross diagram of that. We've got sulfur, and I'm going to try and, because I'm drawing this flat rather than a three-dimensional shape, the three-dimensional shape is like that, you see, but I'm going to try and draw it on paper. I've actually got 1, 2, 3, 4, 5, 6 bonding pairs around the sulfur because I've got 6 fluorines attached. There they are. And since this is a dot and cross diagram, I'm going to show the lone pairs of electrons on the fluorines. But all we're concerned about is the number of electron pairs around the central atom, which is the sulfur. So all we're concerned about are 1, 2, 3, 4, 5, 6. Now you might be wondering how sulfur can have 12 electrons in its outer shell. This is a phenomenon known as expanding the octet, and it basically involves using some of the empty 3D orbitals to accommodate electrons, but that's for another day. Let's have a look at the shape of the molecule then. When you get 6 electron pairs, 6 bonding pairs around a central atom, you can see hopefully that all of the bond angles are 90 degrees, and that again allows the pairs of electrons, these grey sticks, to get as far away from each other as possible. Now, if I want to draw that on a piece of paper, the normal way to do it is to pretend that this fluorine, this sulfur, and the other fluorine are in a straight line, flat on the paper. So I put it like that, and then it's sort of rotated. So the fluorine that I'm holding with my thumb and finger there, and then the sulfur and the fluorine opposite it, they are in the plane of the paper. Then the ones closest to the camera, the two fluorines coming up towards the camera, they're going to be wedge bonds coming towards you, and then the other 2 going underneath the diary, they're going to be shown by dotted lines. So let me show you how to draw that. Sulfur, fluorine and fluorine. Might help if I just take away some of the atoms. So that's what I've drawn so far. The 3 atoms that are lying flat on the page, and then I've got 2 coming up from the page, and I show those as wedges coming out of the page. There's a fluorine and a wedge coming out of the page. There's a fluorine. So they're going to be like that, and then the other 2 are going behind the page, so I draw those with dotted lines. So where did that go? There it is. So I just draw dotted line F and a fluorine there. And the bond angle here is, all of the bond angles are 90 degrees. If you look down the top, you can see 90 degrees, 90 degrees, or if you look that way, 90 degrees. All those bond angles are 90 degrees, whichever way you look at it. Now, in some of the more difficult questions, you come across ions in which you've got 6 pairs of electrons around a central atom, 4 of which are bonding pairs, and 2 of which are lone pairs, and The shape then is a flat square, square planar. I should tell you what this one is. I'll come back to that one. Square planar. So you've got a lone pair above, they're sort of repelling these bonding pairs of electrons down, but equally you've got a lone pair of electrons underneath which are repelling from the other side, so they balance out and you end up just with a flat molecule. So that's square planar. This one is basically, if I was to wrap it up in paper as a Christmas present for you, I don't know how I would do that, but there you go, it would be a diamond shape. But we don't call it a diamond, we call it an octahedron. It's got 8 sides to it, and these sides are all equilateral triangles. So the shape we call it is octahedral. Octahedral. Whereas if I, let's say I got rid of the ones above and below, so that it lies flat on the ground, sort of flat on the page, I would have a lone pair above and a lone pair below. So let's just make that X. Then that shape would be square planar. Just write that down for you. Square planar. But it still belongs in this family of having 6 electron pairs around the central atom. So again, you would say there are 4 bonding pairs and 2 lone pairs. Electron pairs repel, bonding pairs repel more, so it forms this shape. But in this special case, you've got equal repulsion from above and below, so it ends up being a flat molecule. Now finally, if we take a look at the situation where you've got 5 electron pairs around the central atom, the example here is always PCl5, so it's phosphorus 5 chloride. That's the oxidation number of the phosphorus. And if I draw the dot and cross, so you've got 5 electrons in the outer shell of the phosphorus, just like you have in nitrogen. It's in the same group, of course. And then you've got 1 chlorine there, 1 chlorine there, 1 chlorine there, chlorine there, and a chlorine there. And again, I'll just put in the lone pairs on the chlorines, because you've got to do that if asked to draw the dot and cross diagram, the bonding. Again, this is another example of an atom, in this case the phosphorus, expanding the octet. It's breaking the rule that says you have 8 electrons in the outer shell. It's now got 10 electrons in its outer shell, and it's using the vacant d orbitals. Now the shape that one forms, here is a model of it, and if I take away 3 of the fluorines, first of all, you've got the phosphorus and 2 chlorines in a straight line. So if I draw those first of all, so I've got the phosphorus and a chlorines, 2 chlorines, so they're flat on the page, so to speak. And then I put another one on, and that's also going to be flat on the page, you see. So I can draw that with a solid line, and the bond angle there is 90 degrees. Okay, but then when I add the other 2 fluorines, one of them is coming out of the page towards me, so that's going to be shown as a wedge, and the last one is going behind the page like so. So I have to show that with a dotted line. So there we go, Cl. And in this molecule we've got 2 bond angles to think about. First of all, if you just look down from the top, I mean, I can take away 2 of them and show you that we've got the 120 degrees there. So you've got a 120 degree bond angle. I can write it in here. It's also between this one and this one and this one and this one. And if I put back my other two fluorines, you can see that there is also a bond angle of 90 degrees in here. So you've also got a 90 degree bond angle. And the shape of that one, I don't actually have a model of that, but imagine I took away the bottom fluorine, then if I wrap that one up, it would be a pyramid, a triangular pyramid. Where's that one gone? There it is. If I wrap that one up, it would form a pyramid with a triangular base, and but it's like two of those joined together with a common base. So I've got one of those on the top and one of those on the bottom. So it's a trigonal bipyramid, or trigonal bi, because it's two pyramids, pyramidal. Again, just look that up in your textbooks and the specification, because you see different variations on these. But the thing to remember is that it's got two bond angles, 120 degrees and 90 degrees. There's no need to overcomplicate this. If you just stick to this basic master plan, decide the total number of electron pairs in the around the central atom, and if it's 2, remember BeCl2, and the bond angle is 180 degrees and it's a linear molecule. If it's 3, the textbook example is BF3 and it's 120 degrees. If it's 4, the textbook example is methane and it's 109.5 degrees. If it's 5, the textbook example to remember is PCl5, and you've got 90 degrees and you've got 120 degrees. And if it's 6, the one to remember is SF6 and the bond angle is 90 degrees. And the names then, that would be trigonal planar, tetrahedral, trigonal bipyramid and octahedral. And then you can work out the shapes if you successively replace the bonding pairs with lone pairs, remembering that for each lone pair that you have, you decrease the bond angle by 2.5 degrees. And to work out the shapes, just always say to yourself, what would it look like if I wrapped it up with the minimum amount of wrapping paper for somebody? What would it look like? And that's the shape. Very good. In order to complete this topic, I would like to explain to you how to deal with molecules or ions containing double bonds. So I've got the full dot and cross structure of carbon dioxide here, and then this is the structure showing the covalent bonds as solid lines. Now, if you consider this carbon in the middle, you say, well, it's got 4 electron pairs around it, so why isn't it tetrahedral? Why isn't it the same shape as methane? Well, of course, these electron pairs are not able to get away from each other. One pair is a sigma bond on each side and one pair is a pi bond. If you haven't done that yet, don't worry about it. But the point is, you have to treat a double bond as though it's just one region of negative charge. You treat it like it's just an electron pair to all intents and purposes. So it would be like beryllium chloride, 2 electron pairs. And so carbon dioxide has this linear structure with a bond angle of 180 degrees. 180 degrees, and we would say it's a linear molecule. In ethene, you have a double bond between 2 carbon atoms, and again we have to treat the the double bond electrons as a single region of electron density because they cannot get away from each other. Now you can consider the shape around either of these carbons. You could say what's the shape around this carbon or what's the shape around this carbon, but in either case you have three regions of electron density around the carbon, and so the bond angle is 120 degrees, 120 degrees, 120 degrees. Of course it's just the same around this one. Now I know that because you have more electrons here there will be slightly more repulsion and this will be slightly smaller, but that's good enough for A level, for AS. And you can also say that the molecule is flat. These mods are excellent for showing you the shapes of molecules. It's just a flat molecule, so it's planar. Okay. Just want to show you one more example. Propene. Now you've got both double bonds and single bonds between the carbons here. So this part of the molecule is, imagine that was a hydrogen, then it would be a flat molecule and you'd have 120 degrees between these bonds. But if we didn't have that there and had a hydrogen, this would be a methane, which would be tetrahedral. So you've got these bond angles are all 109.5. They are the tetrahedral part of the molecule, and then these bond angles are all about 120, and as are these, so they're 120 degrees. So that part of the molecule is planar, this part is tetrahedral. I can just draw that out for you in a more conventional fashion if that was looked a bit strange. That would be the structure of ethene, but if I put on another carbon then you would have three hydrogens on here, and even without drawing the three-dimensional structure you can say we've got three regions of electrons around electron pairs or electron density, because we've got two pairs here, but three regions around this carbon, so that one would give you the 120 degrees. Similarly here, 120 degrees, but this carbon's got four electron pairs around it, so you would say it is tetrahedral and the bond angle is 109.5.